proteins. It's in our hair, our skin, and our muscles. It makes important enzymes to help us survive, and it builds and repairs our bodies. But how do we make these essential macromolecules? Well, it's a lot like building and shipping toys, like these. Let's get cooking. First, there's transcription. Transcription happens in the nucleus, which is like the brain of the cell. It coordinates cell activities and stores DNA. It all begins here in the nucleus with our set of instructions, in this case, DNA. I'm going to use mRNA, or messenger RNA, to help copy the instructions of the DNA onto my mRNA to take with me. I'm going to need a little help from RNA polymerase. This isn't little. That's better. The magnifying glass, or RNA polymerase, slides across the DNA, unzipping the nucleotides, adenine, thymine, guanine, and cytosine. As it unzips, free-floating nucleotides from around the nucleus match with the opposite strand, then make their own separate strand, which is our mRNA. Remember, in mRNA, thymine is replaced with uracil. This mRNA is an exact copy of the first strand of DNA. It will act as a messenger to be taken out of the nucleus into the endoplasmic reticulum. Then there's splicing. Splicing occurs right before the mRNA is leaving the nucleus. Oh, looks like my mRNA has some mistakes in it. I better use my SNRPs and my spliceosome to help fix those. The mRNA is made up of exons, the parts we need for the protein, and introns, the parts we don't need to make the protein. This is a SNRP. It recognizes the introns as it slides down the mRNA. The scissors represent spliceosomes. It cuts the introns out, leaving us with the exons, the good stuff. Lastly, there's translation. Translation occurs just outside the nucleus, in the ER, which contains ribosomes. It puts the protein together. Here, in the endoplasmic reticulum, outside the nucleus, we take our mRNA and attach it to our rRNA, or ribosomal RNA. Our first three nucleotides, adenine, uracil, and guanine, make our start codon. Next, we have our next three nucleotides, which are represented here by guanine, adenine, and uracil. Then, a tRNA comes along with the anticodon, which is cytosine, uracil, and adenine. This attaches to the codon. At the end of the tRNA is an amino acid, which is represented here by the LECO. This process continues as the tRNA leaves and the amino acids form a polypeptide chain until they reach the termination codon. Now that we've made our polypeptide chain, we need to make it into an actual protein. There we go. This is our primary structure. It's just an order of amino acids. If I fold it like this, whoop, 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 hey. Or I twist it like this, whoop, it'll become a secondary structure caused by hydrogen bonding. Then the amino acid goes into tertiary structure, where there's disulfide bonds and hydrophobic and philic bonds that help make the structure what it is, just like this crumpled piece of paper. Finally, we can also make our quaternary structure. This step is optional, but it's when another protein binds with our protein, and together they make a bigger protein. But for now, we'll just stick with tertiary structure. Time to go to the Golgi body. Oh look, our protein! Here in the Golgi body, we refine and package our protein off to be sent out to the outside cell. Sayonara, bon voyage!